Thank you all for joining us today for the fourth in LCSA series, Assessing the Climate Effects of Biofuels Using Integrated Assessment Models, Part 1, with Richard Plevin. The LCSA series is presented in partnership by the American Center for Life Cycle Assessment and the International Society for Industrial Ecology, and is based on the recent special issue of the Journal of Industrial Ecology on Life Cycle Sustainability Assessment. As you can see on the screen, we have the link to the issue. We hope you'll be able to join us for the last webinar in the series that will be taking place on Wednesday, March 14th at 9 a.m. Eastern. I'm Debbie Steckel. I'm the Executive Director of the American Center for Life Cycle Assessment. And for those of you who are unfamiliar with ACLCA, we are a nonprofit membership organization providing education, awareness, advocacy, and communication to build capacity and knowledge of environmental LCA. ACLCA's membership consists of government, industry, academia, consulting, and NGOs. To find out more, we'll help you visit our website at www.aclca.org. ACLCA offers many activities and resources for our members, including webinars like these, a textbook, certification, and active committees. In addition, we host the LCA conference, and this year it will be held on September 25th through 28th in Fort Collins, Colorado, with a pre-conference on September 24th. We hope you'll check out our website and find out more. Abstracts and registrations are currently being accepted. I'm now going to turn it over to Reed Lipset with the International Society for Industrial Ecology.
Thanks, Debbie. The International Society for Industrial Ecology is a global scientific and professional society that promotes industrial ecology, which, for those of you not familiar with the term, encompasses life cycle assessment, material flow analysis, environmental input-output analysis, industrial symbiosis, eco-design, the circular economy, a whole variety of topics and tools that relate to energy and material flows in the environment and in society. The Journal of Industrial Ecology is an international peer-reviewed journal owned by Yale University and based also at Yale, published by Wiley. It's the official journal of the International Society for Industrial Ecology. I want to let you know that today's paper, the paper on which today's presentation is based, is available for free download, and I'm sending the link to Debbie, and she can send it out to the whole to all the listeners. Thanks.
Okay, wonderful. And just to let everyone know, we will send the link through the chat also, so you'll all be able to access it immediately. Before we jump into today's webinar, just a quick few items on housekeeping. All attendees are in listen-only mode. We will have time for Q&A at the end of the webinar, but please do not wait until the end of the webinar to get your questions in. You can send them in at any time using the GoToWebinar panel and clicking on the questions link. This webinar is being recorded and will be available on ACLCA's YouTube page on Monday. If you have any questions, please send them in the chat box to me, or feel free to send it via email on the email that's on your screen. Now, it's my great pleasure to be able to introduce our speaker today, Dr. Richard Plevin. Dr. Plevin is a research scientist at UC Berkeley's Transportation Sustainability Research Center, part of the Institute of Transportation Studies. His research is focused on climate effects of biofuels, particularly related to indirect land use change and related policies, life cycle assessment methodology, and modeling and uncertainty analysis. Richard is working with governmental, commercial, and nonprofit organizations on modeling biofuel climate effects. I will now turn it over to Richard. Thank you so much.
Thank you, Debbie. Let me get my presentation loaded here. No, I've lost my, there we go. Show my screen. All right, well, thank you everybody for joining us. It's a little disconcerting giving this kind of talk into the void, not knowing who's out there and how many you are, but welcome. I'm going to be discussing the use of integrated assessment models for assessing the climate effects of biofuels. And don't worry, I'll be defining integrated assessment models shortly. First, to put this in perspective, I want to just discuss where most people start from in this work, which is attributional LCA, because what I'll be doing is contrasting what I'm working on using these integrated assessment models for. I'll be contrasting that to attributional LCA and the use of these techniques in policy making. So this is a typical definition from Guinée back in 1993. The idea was that LCA quantifies all the environmental impacts of a product during its entire life cycle. And I've highlighted all and entire because when we start looking at other techniques, it raises questions about whether those statements are actually completely true. The typical life cycle, as it's envisioned, starts with resource extraction, goes through all the production steps, and ends with waste treatment or recycling. Sometimes this is called a cradle-to-grave analysis, and I've just added here a typical kind of figure that's used to describe this. This approach has been criticized in the literature for a variety of reasons, and more recently, the whole idea of life cycle sustainability analysis has come about, which is really a way of improving upon what was done previously with attributional life cycle assessment to incorporate some of the things that attributional LCA has been criticized for lacking. Unfortunately, as with consequential LCA, LCSA doesn't have an agreed upon approach or definition, but it's typically described in terms of, and this is relative to attributional LCA, broadening of impacts so that we're not looking just at a technologically linked input-output chain, but looking more at an economy-wide analysis, broadening the level of analysis to include things like multiple scenarios, and deepening the analysis to include, and it's not clear to me where some of these things end and the next one begin. They seem to have some overlap, but deepening often would be including economic or behavioral relations in addition to technological ones, and dealing with more explicitly with uncertainty and subjectivity in these assessments. My work addresses all of these, but I sometimes wonder if the term life cycle still makes sense when you change the analysis enough so that you're no longer talking about a clearly defined supply chain and usage, input-output relationship-based pathways. Are we still really talking about a life cycle? I'm not sure about that. So where I come at this from is not so much as an LCA person per se, but as an analyst working on biofuels and biofuel policy with the state of California. I've worked with them during my PhD work and have continued to work with them over the years on the state's low carbon fuel standard, which uses LCA to rate different fuels and thereby to motivate the use of hopefully lower climate impacting fuels than petroleum. So the questions that motivate my work include these. Do biofuels, or for that matter, any alternative fuels, actually mitigate climate change, and to what degree? What would be an appropriate performance metric for use in LCA-based fuel policies, such as the low carbon fuel standard, which I should add is not just California at this point, but Oregon has implemented one that's based largely on California's, and the state of Washington is in the process of doing so as well. And this also exists in British Columbia, and there's a variant of it in Europe. And So these are increasingly common. Then the real question I have at the end of the day is, do these LCA-based fuel standards actually mitigate climate change? And you might say there's a different analysis that would be done for each of these, but I think maybe the same approach can be used for all of them. For those of you not steeped in the whole biofuels debate, you might not be aware of this, but there was a very important paper published in 2008 in Science by Tim Searchinger et al. That was really the first one to use economic models to estimate the cascade of effects that occur through markets, agricultural markets, land markets, forestry and timber markets, that result from an increase in the use of land, say in the US, to produce biofuels, and how that perturbs international markets and ultimately can cause the release of carbon that may undo the benefits or overwhelm the benefits of the supposed displacement of petroleum by the biofuels. The number that they produced for this effect, I won't even go into, but it's been criticized for various reasons. The modeling was somewhat primitive by today's standards. But to me, the most important conclusion of the paper was really methodological, which is that input-output technological relationships really don't predict effects. You need to actually model effects. Cause and effect relationships are the important thing to model, and that's missing from the standard kind of LCA that they were contrasting their analysis to. In this case, they were looking at the GREET model from Argonne Labs, which is an attributional LCA model. So to break this down just a little bit more, if we start on the left here, I don't know, perhaps my mouse cursor shows up. Let's say a new biorefinery is built, and in the Midwest, where they tend to be built, and a US corn farmer previously selling his corn into the feed market decides to sell his corn to the biorefinery. The next thing in this modeling scenario, the next thing would be that corn exports would go down because the total amount of corn being used in the economy has increased. And this would cause a price change, which causes some combination of three effects. One of them is intensification, where farmers will use more inputs to increase yields. Because the price is higher, they can afford to put more fertilizer on their crops, for example. There will be some substitution effects, where if you can find a cheaper feed for your cattle, you might use that instead of corn, which is becoming expensive, so you use less. And then the one that we're most concerned with here for the climate effects is extensification, which means using land that wasn't in crop production, bringing it into crop production. And this is typically involves clearing the land with fire, churning up the soil to till it, and this results in the loss of both biomass and soil carbon, which can be pretty significant in quantity. And this is what the Searchinger analysis was the first one to try to estimate this effect. To give you an example of why this is important, sort of a preview from the GCAM, the Global Change Assessment Model, which is the IAM I've been working with. And you can see on the right, this is just the effects of corn ethanol production, an increase in corn ethanol production on the 6 elements below. It's not the entire fuel production process. It's just looking at these agricultural effects and land use change effects. If we look at where they occur, you can see that most of it occurs outside the US, and this is mediated by agricultural markets and changes in prices. So you get some effect in the US, but the bulk of the effect happens in the rest of the world, which is why it's important to use global models that trace effects through economic markets in order to see what's going on here, or at least to project what may be going on here. So we've talked a little bit about attributional LCA. To contrast that with consequential LCA, attributional LCA if you think of the word attribute, it's trying to attribute to a specific product system some portion of the total pollution, energy use, material flows that occur in the economy at any point in time. It's trying to attribute some portion of that to a specific product system. And that's done by tracing this supply chain. That's the standard approach. The other modeling approach is consequential LCAs, which is looking at how the flows of energy and resources to and from the environment actually change as a result of a decision you're going to make or a policy you're going to implement or some action you're taking. So one of them is trying to sort of divide the global use of energy and materials and assign portions of it to different product systems. And the other approach is trying to determine what changes as a result of an action. I like these very simple figures from Bo Weidema. I think they're helpful. Just to point out how different these two analyses are. Consequential LCA might allow us to ask, what is the net climate effect of using more of some fuel X, corn ethanol or soy biodiesel? And what we're looking at are the perturbations on the system, as indicated by that graphic. And again, attributional LCA is trying to attribute a portion of the overall effect to some fuel system. Really importantly, these are totally different types of analysis. They are looking at different things. They have different life cycle inventories. They have there's no reason to expect that these two analyses of the same product should come up with the same answer. Yet, from my perspective, I often see attributional studies being used to answer the question that's here associated with the consequential LCA. And it doesn't really answer that question. You might think it's a proxy for that analysis, but it isn't necessarily a good one. And this has been the focus of some of my work in the recent years, trying to peel this apart. So to model biofuel consequences, the first question is, what kind of consequences are we talking about, and how would we go about modeling them? The idea is to use a model that represents the global systems that we think are important, and those include, in biofuels, those include the agricultural and forestry markets, land markets, energy markets globally, because the greenhouse gas emissions we're dealing with are well-mixed global gases, so it doesn't matter where they're emitted, they have the same effect. And we want to trace these global market effects where they occur, and then see what the changes in energy use and land use and emissions are resulting from this. When you have a model like this, any increase in production requires you to effectively implement a policy. That might be a carbon tax or a mandate to increase biofuels by a certain amount, but ultimately at the end of the day, you're not examining a product system as much as you're examining a policy. And the reason that's important is you can increase, let's say, soy biodiesel production by 1 billion gallons a year in a model a variety of ways. You can tax fossil carbon, you can subsidize a specific technology, you could have a mandate that forces a certain volume to be produced and see how the markets respond to that in terms of the price changes required to make that occur. And the policy choice that you use to, the term of art is to shock the model to increase the biofuel production, actually changes the result at the end, because these things have effects on other related markets that differ. So I guess the point I'm trying to make is that even if you think you're modeling a product system using this approach, you're ultimately really modeling a policy that drives a change in a policy, in a product system. And when we say consequences, what we're talking about is the change in some climate relevant metric from some baseline scenario without the policy compared to a new scenario with the policy. So what we're looking for is, how do the modeled results change when I add this policy to the system? There have been a number of ways that people have addressed consequential LCA with biofuels. One of them, Dalgaard and Schmidt, used reasoning or their understanding of markets to identify the marginal product and the marginal supplier affected by a change in biofuel production. In a sense, it's a shortcut to what the economic models do. They just examined the markets and determined what they thought would be the marginal product and supplier. Problem with that approach is there usually isn't just one. There could be a number of different products and suppliers affected, and the economic modeling approach tries to capture more of that. Other approaches have used ag sector partial equilibrium models and combined these with emissions data. Notably, the US EPA did this in their analysis for the renewable fuel standard. Partial equilibrium models are economic models that look at one or a few sectors of the economy, and the equilibrium that it refers to is a supply and demand equilibrium. Basically, you're looking for the prices that cause the markets that are represented to clear so that supply and demand balance out. And it's partial in the sense that it doesn't try to include all sectors of the global economy. So, for example, it might just be the agricultural, forestry, and energy sectors, but nothing else. To contrast that, you have computable general equilibrium models, which do represent or attempt to represent the entire global economy. One that's been used a lot for biofuels analysis is the GTAP model, the Global Trade Assessment Program model. D'Andres used this combined with the EcoInvent database to estimate the effects of changes in biofuel production using GTAP, and then using the changes in the different industries that GTAP predicts, use the EcoInvent model to convert these into environmental effects. Similarly, Earls et al. Used a forest sector model that was another partial equilibrium model with EcoInvent. Menton more recently used an energy system model. If I remember correctly, this was of the French energy sector, and used some emissions factors with that. The approach that I'm talking about here that we're heading towards after this sort of long introduction is to use integrated assessment models for this kind of thing. The advantage being that the emission factors and environmental outcomes, at least the climate outcomes that we're interested in, are built into the model. So it doesn't require marrying some economic model to some emission model. Instead, you have a system that's integrated from the get-go. When we say integrated assessment models, that can cover a wide class of models that really could include anything that integrates across disciplines. What I'm talking about with integrated assessment climate models usually are broken down into two categories. There's the top-down flavor, which are highly aggregated, often, some dozens of equations in the simplest cases. They have little or no technological detail, and really what they're good for is estimating the social cost of carbon or looking at the effect of a carbon tax, but they're very high level and top down. And the three listed here, DICE, PAGE, and FUND, were used by the interagency working group in the US to estimate the social cost of carbon for US policy purposes. The other kind is bottom-up, which are all still they're still aggregated, but they're less aggregated than the top-down models. They offer more technological detail, multiple land classes, and they allow you to model technology-specific policies because they have specific technologies modeled, right? So some of these include GCAM, which is the one I'll be talking more about, and a whole range of other ones that have typically been used in the IPCC reports and other assessments. So the reason I think these IAMs are useful for examining the biofuel policies is that they're really designed to assess climate change policies. They track greenhouse gas emissions, and they also generally take this to the next level of radiative forcing, and often to change in temperature, and sometimes even to monetized damages, which can be useful ways to integrate these effects in addition to just a total emissions of greenhouse gases. Because they're climate models, they have a global scope, and they model the economic interactions. In this case, the integration in these IAMs is over the energy sector, the land use, and economic, the economy. So they do account for price feedbacks. Energy supply and demand is is computed by the model, it's endogenous. Typically, they'll represent crops and forestry and livestock production separately, and in many cases, unmanaged land that may be converted into those uses. And more generally, land use change and the emissions from the conversion of land as an important factor. These models are often dynamic, which means that they don't just run once and produce an answer. They are run over a time horizon at some time step. For example, a model might be run starting in 1990, and then it'll produce an answer which will be the input for then the analysis for 1995, which will be the input for the analysis for 2000, and so on. So you have this sequence of re-equilibration that happens in each time step based on the results of the prior time step, and some exogenous factors that may be changing, like global GDP or global population. And these models, again, offer a number of policy levers. You can typically model subsidies and taxes on different types of products or on different greenhouse gases. You can have mandates to produce at a certain level. Let's see, I think I need to pick up the pace. So I think there are a lot of advantages to using IAMs, many of which I've just described, but there's also limitations relative to what we would consider a typical LCA, in that these models don't generally include things like recycling or end of life. They don't have explicit representation of supply chains, although in many cases, portions of the supply chain are actually represented explicitly. They tend to have a long-term focus, and in many cases, they're partial equilibrium rather than general equilibrium, and then you get into debates between economists of which type of model provides a more realistic answer. And some of these models have a relatively simple representation of the economics compared to the the analysis of the emissions from energy technologies. The GCAM model, it comes from the Joint Global Change Research Institute, which is a joint institute between the Pacific Northwest National Lab and the University of Maryland. It's an open source model written in C++. Anybody can download it and run it. One of the reasons I like working with it is that it's accessible. Many of the models that are in this space are owned by some developers or by some group that really, they're the only ones who run the model, and you can't really run it on your own. GCAM is not like that. So GCAM takes this kind of information in the green, things about technologies and policies and physical resources, and through a series of model equations and parameters produces estimates of changes in all of the things in yellow on the right. And as you can see, most of these are relevant to the biofuel question. So specific limitations of GCAM relative to typical LCA systems are that its technological representation is generally simpler. They're made, for example, in GCAM, for example, there's only one corn ethanol technology, even though there's several of these in use around the US and other places. But there's one representative technology for producing ethanol from corn or from biodiesel from soybeans. That, of course, could be made more detailed if you wanted. I have some question about whether that's valuable or not. We'll get to that later. As I said, there's no explicit representation of the supply chain. There are the portions of it that are represented really are the ones critical to energy use and commodity use on the agricultural side, because those are the markets that the model represents explicitly. In terms of biofuels, one limitation is that GCAM only has one refined petroleum product. There's no distinction between gasoline and diesel, for example. And its trade representation is fairly simple. Only primary commodities are traded. For example, corn is traded, but corn ethanol is not traded. So the real world flow of sugarcane ethanol from Brazil can't be represented directly. You could trade the sugar between Brazil and the US and produce the sugarcane ethanol in the US, but once produced, the sugarcane ethanol can't leave Brazil. Again, this is a limitation of this model, I'm just pointing out. And in the current version, there's no way that increases in prices can trigger increased yield of crops, which has been an important factor in the discussions about modeling land use changes in the policy space. This feature is coming in the next version of GCAM. Basically, the idea is as prices rise, you can afford to put more fertilizer or to increase irrigation on your crops because you can do so at a profit now that you couldn't at the prior price. So I'm going to be discussing an analysis that I've been doing with GCAM, and it's the point at the bottom here is really important. I'm not trying to estimate the right estimate for carbon intensity of a biofuel to tell you that I now have the answer because I'm using this model and it's better than all other models and it's scientifically flawless. I mean, that's certainly not the case. What I'm really curious to know is how the carbon intensity of biofuels differs under different assumptions, different definitions of exactly what is carbon intensity, different assumptions about policies that might be in place or not, different ways of, different results that may come from variation in parameters that are uncertain. So basically a sensitivity analysis. And again, going back to my motivating questions, with the numbers that are coming out of these models being plugged into public policy as the number that actually drives the relative use of different fuels, the lower carbon intensity means it's, quote, better and therefore more of it should be used. How reliable are these numbers and how dependent are these numbers on all sorts of assumptions and subjective choices and definitional changes that underlie these models? It's, I think, important to peel back to look at this and not just say, oh, we're using LCA. Really, the devil is in the details. So here are some of the factors that affect carbon intensity estimates in a model like this. Well, of course, the first is, and the most important, is which model are you going to use? Then over what period are we going to analyze the model? Are we going to look at 10 years, 20, 30, 100? Are we going to look only at the standard 3 greenhouse gases, CO2, N2O, CH4, or are we going to include all sorts of things that affect climate? What other climate policies do we assume are in effect? What do we think about other land demands? And an important factor here is how, over time, crop yields may be changing in response to climate change. In other words, estimates made based on historical data may not be valid in the coming decades. And all of these land uses, food and bioenergy, are competing for the same land. Let's see. there's more here, but in the interest of time, I'm going to go ahead. So my working definition of biofuel carbon intensity is it's the sum over a number of things, which we'll discuss in a moment, of the emissions, the change in emissions associated with an increase in biofuel production, divided by the sum of the change in production of that fuel over the same time period. So you've got to define a time period. You run your model and you count up all of the emissions in the base case and then in the policy case for some category of emissions, and that's up, that differs across policies. And then you divide that by the total increase in that biofuel that you're shocking, that you're evaluating. And this is typically expressed in policy in terms of grams of CO2 equivalent per megajoule. And the summations just are occurring over the various regions in the model and across the various sectors. And then the chosen greenhouse gases, which may be all Kyoto greenhouse gases or just the 3, or it may be not even just gases. It may include things like albedo change, reflectance of land cover. So there's an interesting issue that comes up as we move from the model that was used by California in its modeling of land use change towards a model like an integrated assessment model. In GTAP, there is no representation of time, and this may surprise people. The way the model is used, it starts out with a database that represents an equilibrium state of the economy, everything, all supply and demand match. Some shock is introduced into the model, for instance, an increase in biofuel production, and the model is allowed to re-equilibrate around that change so that all the prices are produced that cause the market to balance out again. There's no time element in there. It's sort of modeled as an instantaneous change. So when we want to turn this into a carbon intensity, we apply an assumption of, in the US anyway, 30 years of fuel production, and we total up emissions that we think would occur over 30 years starting at this shock, and we divide it by by basically 30 years, 30 times the size of the shock, and that's our carbon intensity. And I point out that Europe has decided that 20 years is the relevant time frame, and this ends up being one of the most important factors in determining carbon intensity. In GCAM, because it's a dynamic model that operates over time, you have a different approach. For one thing, the fuel shock doesn't have to be a single shock. It can occur in pieces over time. There can be a ramp up to an increase in biofuel production over time. And additional land use change may be induced at any time step in the horizon you're looking at. So it turns out that the shape of the ramp up curve matters. So in my analysis, I looked at a couple of different shapes that I just simply called fast and slow. The fast one gets up to a level of 4.5 billion gallons quickly, and the slow one, takes 15 or 20 more years to do so, but then holds at that level over time. And it turns out, I should say that it holds it at that level over time, and the final 40 to 60 years, 2040 to 2060 is constant. But I also vary the time horizon so that I pick up a different portion of that 2040 to 2060. So I may look at only 20 years starting at 2020, or I may look at 40 years, and that also ends up being important. I ran this under a Monte Carlo simulation with about 50 parameters being adjusted, and ran 5,000 trials on a Linux high-performance computing system, a computing cluster. And the shocks were introduced by forcing a level of output. And the way this works in GCAM is the model computes the tax or subsidy required to meet that production level, and it affects the prices that way. The specific parameters I used are here. We can come back to them if there's time, but let me just move forward. I tracked carbon intensity from each of the Monte Carlo trials as using the definition I described. I also tracked rebound effect on global fuel use. Usually baked into attributional LCA is the idea that if I create more biofuel, I am necessarily displacing or avoiding exactly the same energy quantity of gasoline. And when you look at the modeled results from a number of models, that's not how it works out exactly. You don't quite displace as much as you produce, and you don't just displace petroleum-based fuels. You may displace other biofuels. So the other thing I tracked was radiative forcing over time, which is just allows the model to aggregate all of the greenhouse gas emissions over time in a coherent way, rather than just applying global warming potential factors. So these are the radiative forcing plots that come from this. The light blue region around the line is the 95% confidence interval around the median. And what you see here, this is over the 50 parameters being adjusted. So I think it's very difficult to say that we have any single number that is more meaningful than any other, but the overall message that this gives us is that in the case of cellulosic ethanol, most of the time, most of the trials produce negative forcing, which means cooling. And for corn, most of the time, it produces positive forcing. So in very general terms, the cellulosic ethanol looks like a reasonably good bet to mitigate some amount of climate change, and the corn doesn't. Now, of course, that's just one model, but this is the effect over a wide range of parameters. So it's I think, much more interesting than looking at just any point estimate, where you could argue till the end of the day over what the right parameter values should be. So one of the things you can do with this kind of analysis with the Monte Carlo is to look at the contribution to variance of different uncertain parameters in the model. And this is basically a normalized rank correlation of each of the inputs to the output of interest. So we're seeing which ones correlate more, which inputs correlate better with the output that we're interested in. In other words, they seem to travel with it in the same direction or in the opposite direction more consistently. And as you can see, the analytic horizon, which I varied from 20 to 40 years, turns out to be the top contributor to uncertainty. There, if we go down a little further, you see whether there's a carbon tax and how much the carbon tax is also important. The ramp index, which is the fast or slow factor, is also important. So, as well as some of these other more technical factors, like the carbon density of soil and under unmanaged forests or under crops, the uncertainty in these things are important too. But what I find interesting is that half of the top 6 parameters are really model choice or subjective, depending on how you want to look at them. And they aren't really just the typical kind of parametric uncertainty in our estimate of carbon intensity. Part of the problem, in other words, is that the definition of carbon intensity is not clear, and it matters how you set the problem up. You get different results. Similarly, for cellulosic ethanol, turns out that the biomass coefficient is important here. That's how much biomass is required to produce a certain amount of ethanol, and that really is a big driver of land use change, because that range is wide. The more biomass you need, the more land you need, and that just ends up causing a large effect. But the analytic horizon and the carbon tax remain important. And if we look at just the land use change emissions, and the reason to do this is because some of the models, like in California's low carbon fuel standard, use only this, as opposed to all of the changes in emissions across the economy. So just looking at the land use change emissions, this is the range that we get for these two fuels. And just want to point out that a range that we got for corn ethanol in a previous GTAP modeling study almost does not overlap with the results from the corn ethanol in this GCAM study. So what that tells you is that your choice of model is critically important. We don't even have much overlap in the distributions over these Monte Carlo studies. Interestingly, the rebound effect, it's almost the same for the two fuels, but a little different, and that's because of price differences in the fuels. But it's almost always positive, which means that there's less than perfect replacement of petroleum. And if we look at the overall net effect of CO2 in all sectors as our carbon intensity metric, which includes the displacement of refined petroleum fuel. So this is not a number that you would compare to a petroleum fuel because it's already built in. The displacement is already built in. What we see is similar to the figure with the radiative forcing. Cellulosic ethanol is mostly below zero, which means it's a net reduction, and corn ethanol is entirely above zero in this. So in terms of the rebound effect, a couple of interesting things come out of the model. One is that this green area that's below the zero line, which is the oil refining, and again, there's only oil refining, there's not separate gasoline and diesel. That green bar is smaller than the orange bar above the line, which is the increase in corn ethanol production. So we're displacing less, and these are in energy terms, not gallons. So the energy density differences are accounted for. There's less reduction in oil refining than there is increase in biofuel production. And the corn ethanol increase also displaces some other biofuels. And this will be the way the markets work out in terms of prices, price equilibration. So the assumption that you're just going to perfectly displace everything, it really doesn't hold. I'm going to skip over this. And that, let me just jump here so we have some time for questions. As I found in other analyses, continues to be the case that really carbon intensity suffers from what some have called the fallacy of misplaced concreteness, which is that it's treated as if it's a concrete fuel property when in fact it isn't at all. It really is based on many assumptions and subjective choices. Rebound effects are generally positive, which means we don't displace as much petroleum as would be hoped. The use of radiative forcing over time really provides a good way to make explicit the time assumptions in the model, because you can see at what point that line might cross zero or not. And the results regarding the fuels we've already discussed. Of course, neither result is definitive. And I'll finish here with a couple of questions of my own, which is this type of analysis still actually LCA? And does it matter? Is this the analysis we should be doing for policies? And given the uncertainties and subjective nature of many of these drivers, how important is it to add further detail to this type of model to make it more like an LCA model in terms of detail? Would that be overwhelmed by all of the other uncertainties? And more generally, is there really a solid basis for using LCA as the driver for a policy? And my own publications, if you've seen my most recent paper, the answer I come up with is actually no. And then if not, what role should industrial ecology play in policy design and implementation? So that's where I'll stop. Thank you.